Chapter 10 of our textbook is all about the properties of circles, and Chapter 10 begins on page 651 with 10.1. And 10.1 mainly goes over definitions as well as two theorems with tangent lines. So first and foremost, we need to know symbols and really the difference between a couple of these terms. So we have a center point, and I'm going to go ahead and name that center C. Alright, circles are named by their center. So if I had circle P, that's circle P right there, that means the center of the circle would be point P. Alright, a tangent line, tangent touches. A tangent line touches. So this line can have a name, we'll call it AB. Alright, and AB is a tangent line, and right there, let's call that K. K is the point of tangency, so exactly where it is tangent. So tangent touches. A secant, however, a secant cuts through. So this is JL. JL cuts through. So JL is a secant. However, JL, there's a difference in these symbols right there. Alright, one means a segment, one means a line. JL is a chord. A chord has two endpoints. That means it does stop on the edge of a circle. Alright, so JL is a chord, and line JL is a secant. And I'm going to have a diameter as well. A diameter does have two endpoints, LM. LM is a chord, but more specifically it is a diameter, and CM would be a radius. So we're going to use tangent, the tangent lines that touch, for two theorems. Theorem 10.1 says if I have a tangent, so here is my tangent line to the right, in blue now. Right? If I have a tangent line, the radius that hits that point of tangency right there is going to be perpendicular. So we're going to use those to create little right triangles, and maybe use the Pythagorean theorem in order to solve for the radius or side or something like that. Alright, and theorem 10.2 says if I have a point out here, I have a point outside of a circle, there are two tangent lines. There are two tangent lines that can be drawn that touch, that swipe the side. Two tangent lines, and those tangent lines are in fact going to be congruent. So whatever their values are, let's say this is 3x plus 4, and this is, let's go ahead and say 31. Alright, I can set those values equal. 3x plus 4 equals 31, and I can certainly solve for x. X would equal 9 here. Whatever values you get for x, now you may have to factor or FOIL. Please make sure you go back and check those values, because sometimes you may get an x equals -2, and if you plug in -2 back in, clearly you would get a negative value for a length, and that wouldn't make sense. So double check the answers that you get there. So really overall in 10.1 you need to be able to identify all of those different terms, and when lines are tangent, you have two tangent lines that are going to be able to be created from an exterior point, as well as right triangles. Alright, so let's move on to 10.2. In 10.2, we start the discussion with the measurements of arcs by using central angles. So keep in mind there are differences between central angles and inscribed angles. So central angles occur at the center. So right here, if I were to name my center K, alright, angle A, KB is measure is 120 degrees. So we have a theorem, and it says that the measure of the arc, now that's different than length, so it's still going to be in degrees. Alright, the measure of arcs are their corresponding arcs are congruent to their central angles. So for example, this minor arc, which means it's less than 180, minor arc AB its measure is going to be 120 degrees because it corresponds to that angle. It's created by that angle. Alright, and I also have something called a major arc. A major arc would be what is left over in the circle. So, for example, arc A, D, B. So I have to move from A, D to B. Alright, in that order. It's going to be 360 degrees minus 120 degrees. So that puts it at 240 degrees. That would be a major arc. It's going to be everything that's left over after you take out that minor arc. In a semicircle, if a circle is chopped in half with a diameter, that means dB is a diameter, anytime you have one of those, that corresponding arc from dB, so you can go either way on this, so D to B here, or D to B, it's the same measurement, is going to equal 180 degrees, exactly half of the circle. So the question here is, one of the bigger questions is, when I name arc AB, which one am I going to talk about? Am I going to talk about that arc or the bigger one? You're always going to want to choose your smaller minor arc as we want to move the shortest distance. So always pick the minor arc if possible. And you should be able to add and subtract different arcs. So let's go ahead and say right here, angle AKD. If I know BD is in fact a diameter, then I know that this is going to be 60 degrees. And if I give this DKC to you as 55 degrees, you should be able to figure out that this is going to be 125. So you should be able to add and subtract and be able to figure out the different names. In 10.3, we have, starting on page 664, we have 4 theorems. And what's really important is we need to just be able to apply these theorems. Alright, so 10.3, what it says is if I have 2 congruent circles, or in the same circle, if I have 2 minor arcs are congruent, then I know their corresponding chords are congruent, or if I have 2 chords that are congruent, their corresponding arcs are congruent. So if I'm given that arc DC and arc AB are congruent, I know their chords are congruent, or if I know that AB is congruent to DC, then I know their corresponding arcs are congruent. And theorem 10.4 says, if I have a perpendicular bisector, I have 2 chords, which mean their endpoints are on the circle. I have a perpendicular bisector, so one of the chords is cut in half. Then I know that the chord that's not cut in half is a diameter. And the theorem that goes along with that, theorem 10.5, says if I do have a diameter, so it passes through the center, and another chord that is perpendicular to it, then I know it's a bisector. So I know that DH is congruent to FH. And last but not least, theorem 10.6 says in the same circle or in congruent circles, 2 chords are congruent. So 2 chords are congruent. AB would be congruent to CD if and only if they're equidistant. So I would have to know that either those pieces are congruent, so FE equals EG, so their distance to the center would be congruent. Then I know the chords are congruent, or I would know that AB is congruent to CD, and that would tell me that those pieces are congruent. So it works both ways. So really here, I'm just setting a whole bunch of values equal in order to solve for missing variables. And I'll get to a couple examples at the end of this video. In 10.4, starting on page 672, we are introduced to an inscribed angle, and this is where some of you will get confused between an inscribed angle and their relationship to an arc and a central angle. So an inscribed angle occurs on the edge, alright, versus the center. So pretty explicitly right to the right of your screen, you can see a central angle, and you can see an inscribed angle that goes with the same exact arc. You can see that the inscribed angle is smaller, and that would be correct. So the inscribed angle is actually going to be exactly half the size of the central angle that would go to the same corresponding arc. So let's go ahead and say that this arc right here, it's 80 degrees. That would make the measure of this angle 40 degrees. So you should be able to find measures both ways. If I go ahead and say that this is 35 degrees, then you would double that and you would tell me this is 70 degrees. In this section, I have 3 theorems, and the first one, theorem 10.8 on page 673, it says that if you have 2 angles, so here I have my red angle and my yellow angle, and they actually both correspond to the same arc. It says that those 2 angles are congruent, so you should be able to see that and know that. Theorem 10.9 says that if you have a right triangle, so that means I have a triangle and I have a right angle, then the hypotenuse is a diameter, or you know that the hypotenuse, the longest side, one of the sides, is a diameter, then you know the opposite angle here is the right angle. So you should be able, given one of the measurements of an angle, be able to find your missing angle, because you should know that right angle is always opposite of the hypotenuse. And theorem 10.10 says that if you have an inscribed, which inscribed means drawn inside, an inscribed quadrilateral inside of circle, the opposite angles, so angles A and C and angles B and D, are supplementary. That means if I were given this angle, let's see, I were given angle D and it's 97 degrees, I should be able to find X by taking that away, so 180 minus 97, and that would give me 83 degrees. Be able to find angle B. So I can put in 2 unknowns here, and let's say this is 78. Alright, I should be able to find that angle A is 102 degrees. Alright, so it's really just all about applying what we're told. In 10.5, starting on page 680, we actually have 3 theorems. The first of which, theorem 10.11, says that if you have a tangent line, so A would be my tangent line to a circle and it intersects a chord, then the angle formed, so let's go ahead and say this angle here formed, is 1/2 the measure of its intercepted arc. So let's go ahead and say, I don't know, that's about 100 degrees. Then that would make this angle right here 50 degrees. And so that being said, if I have this circle, this piece of the arc left over, that would make this 260 degrees, which would then in turn make this 130 degrees. So they should be supplementary as they make up one line, so that works out. Theorem 10.12 says that if you have an interior angle, so let's go ahead and say here's my interior angle X, then what you do is you add the 2 corresponding arcs together and you average them. So I would do arc CD plus arc AB, and then I would times them by 1/2 or divide by 2 in order to work out that angle. Keep in mind that those are vertical angles, and those 2 angles would be supplementary, so X and let's go ahead and say Y would be supplementary. So you need to keep in mind what pieces you have and what you don't. For theorem 10.13, we actually have 3 different choices here. So you either have 2 tangents, 2 secants, or a tangent and a secant. However, instead of adding the arcs, I'm going to be subtracting the smallest arc from the biggest arc. So it's going to be your big arc, your red arc, minus your small arc, whatever that is, and you're still going to divide that by 1/2. Alright, so that's pretty much sums up 10.5. Let's move on to 10.6. In 10.6, starting on page 689, we have 3 theorems. Theorem 1014 says that if you have 2 chords that intersect inside of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segment of another chord. So an example here would be if I talk about chord AB, I take the product of those 2 segments, 2 times 6, and that should equal the product of each segment of chord CD, so x times 3. So this would give me 12, 3x, and x equals 4. Alright, so I should be able to do a problem like that. Theorem 10.15 says that if you have 2 secant segments that share an endpoint outside of the circle, so there's an endpoint outside the circle and there's 2 secants, then the external segment equals the product of the length of the other secant segment and its external segment. So really what this says here is you need to be looking at your short pieces. So if I take my short piece outside of the circle, so outside, times my entire secant, so let me give these labels, A, B, C, and D, E. So if I take AB, so my piece outside, times my entire length, that should equal my other secant. So my piece outside, AE, times my entire segment, AD. So outside times entire, outside times the entire. Alright, and theorem 1016 is similar, where you are going to take the piece outside, so let's go ahead and say A, B, C, D. You're going to take the piece outside, BC, times the entire length of AC, and this only has one piece over here, only one segment, as it's a tangent. This one's a tangent, not a secant. So we're going to go ahead and square it. We're going to multiply it by itself and we're going to square it. This deals with the actual lengths of these segments. And last but certainly not least, 10.7. Starting on page 699, we have the standard equation for a circle, which is x minus h squared plus y minus k squared equals r squared. So here, your center is going to be h comma k, and your radius, r is your radius. So please remember how to input your different pieces. So for example, if my center is 1, 2 and my radius is 3, I want to do x minus 1 squared plus y minus 2 squared and 3 squared, which is 9. Go ahead and actually work that out for me. If I have a center that is negative, let's just go ahead and make it -2 this time. Then I know it's going to be x minus 1 squared plus y plus 2 squared, and let's make our radius 4. The other side's going to equal 16. So you need to be able to put in that information into the standard form, as well as pull the information out. So for example, if I were given x squared plus y plus 1 squared equals 4, I would know that there's no value there, so that means my x-coordinate's going to be 0. And since it's plus, it's always opposite on the inside, so that's 0, -1 is my center. And my radius is the square root of that, because that's 4 equals r squared. So I needed to take the square root of both. R equals 2, so my radius is 2. This is how I would want to see the information. Actually write out the r squareds and give me my point and a radius. Alright, now I'm going to upload another video and work through some examples.